the topic for today, we're going to be looking at DNSSEC. And DNSSEC, we've just been talking about DNS and discussing a number of attacks on DNS. And DNSSEC was invented to try to provide security for DNS. So DNSSEC is a deployed system that is partly used on the internet today. That uses cryptography to ensure the integrity of results of DNS lookups. So in other words, when you look up a host name and get back an IP address, if you're using DNS, it's hard to be confident of the integrity of that. But if you're using DNSSEC, then integrity should be guaranteed. Okay. All right. So here's a little warm up to test how chat is working. Share with me on the Zoom group chat what attack is DNSSEC trying to prevent? Maybe give me an example of an attack DNSSEC is designed to prevent. Yeah, good, good, good. Yeah, lots of great stuff on chat. Absolutely. So designed to prevent man in the middle. If there's a man in the middle attacker who is on the route where queries are being sent and is modifying responses, DNSSEC would defend against that. DNS spoofing, where the DNS caches are poisoned, designed to prevent that. Blind spoofing, the Kaminsky attack that you saw in last lecture, designed to try to prevent that. Yeah, all sorts of spoofing. Great. Okay. So that's what DNSSEC is aiming for. And in this lecture, I'm going to tell you about how DNSSEC works. So the challenge here is when a client looks up a name with DNS, how can they trust the answer that they get back? The first idea that might occur to you is to say, aha, I learned about cryptography. I can use cryptography to encrypt all communications over a connection. So let's encrypt all the communications over the connection. And if you know anything about HTTPS on the web, you might be thinking, oh, let's do the same thing as the web does for encrypting connections. And that thing is called TLS, okay? So TLS is an existing technology. Basically what TLS does is it encrypts a connection. If you have a TCP connection, you can use TLS, and then TLS will do a public key exchange using public key cryptography to exchange a session key between the two endpoints, and then use symmetric key encryption and a message authentication code to protect all the data that's sent over that connection. So we'll see more details about TLS later in this class. But for now, it's a very simple idea. And you could imagine, why don't we, whenever we do a DNS lookup, whenever we send some data and get back some response, let's use TLS. Okay, let's use this method. So this is the kind of the baseline idea that might occur to you for how to protect DNS. And let's look at how well this would work, what it would look like and what the trade-offs are. So let's take this diagram that shows the lifetime of a DNS query. And imagine that we're using something like TLS to encrypt for every connection that's made, encrypt and authenticate all the data that's sent over that connection. Well, there's 1, 2, 3, 4 connections happening here from the original host to the resolver and from the resolver to each of the DNS servers. And so what we would do is we would just set up an encrypted version of each of those 4 connections. So we would have the connection between the host and the resolver would be encrypted using one key, and we'd use public key cryptography between those two to exchange a session key and encrypt and authenticate all those messages, and separately for each of those other 3 connections. All right, so that's kind of a basic idea. Let's talk about how well that would work. Well, this is a natural idea, but it's not a very good fit for DNS, it turns out. It has a number of downsides. One downside is the performance is pretty poor. TLS is fairly expensive. It does public key cryptography when you set up each connection. That's a pretty expensive operation. We'd be doing that every time we made a DNS query, so it'd be kind of slow. And that would be perceivable as a slowdown, because anytime you opened a new website in your browser, it'd be doing a DNS query, and that DNS query would be doing all these public key exchanges, and that could be kind of slow. Also, it's not clear how to support caching if we took this approach. And caching is really important to make DNS scale and perform well. And so the authentication aspect of things is a little tricky if we're using caching, because I would have an encrypted connection with the cache. But that cryptography would only go to the cache, and the cache actually got its data from somewhere else. So how do I get assurances that the cache, the data the cache is sending me is correct? Well, the cryptography wouldn't do anything about that. The cryptography would ensure that data is not being modified between when it's sent from the cache to me, but it doesn't ensure that the cache has the right information. So it wouldn't do anything to stop these cache poisoning attacks we saw last lecture. And from a security perspective, we would have to completely trust the resolver. If the resolver was malicious, it'd become a man in the middle that could attack us despite all the cryptography. So this is sort of not a very satisfying solution. And what it hints at is the distinction between what I might call object security versus channel security. Encrypting a communication provides security for that one channel, but we have in this picture back here, we have 4 channels, and we're encrypting each one separately. And so it doesn't really provide security for the data, the whole lifetime of the data. It only provides security for while it's in transit between 2 servers. So channel security isn't really appropriate here for a DNS. What we really want is we want something I might call object security. The data that I get back from a DNS query, I want to know that I can trust it. That record that says the IP address of google.com is such and such, that's the thing I want to trust. And even though it had was transmitted over multiple connections and multiple servers, I still want some assurance of it that's broader than any one connection. Okay, so this first baseline idea isn't a very good fit for DNS, and we're going to develop one that is a better fit. Okay, so what we're going to do instead is we're going to try to make DNS records, DNS responses, more like certificates. And certificates, when we looked at certificates, the cool thing about them is they're verifiable. They're sort of self-verifying. They have all the information needed when you receive it for you to verify that you can trust the data in that certificate. So certificates are really cool. So we're going to try to do something like that, but now for DNS, where we want a DNS result to be verifiable so that anyone who receives it can verify that they can trust it. Okay, so that's what we're going to try to do. And what I thought I'd do is let's have us design it together. We all in this class are going to together design DNSSEC with that basic idea. Okay, so I want you to think about how you would do this. Here's the setup. Imagine there's a resolver that's making a query, a DNS query. It's asking for the IP address of mail.google.com. And it's asking the name server for google.com. And the name server for google.com knows a bunch of different host names and their IP addresses, and is going to respond with the IP address for mail.google.com. Okay, so think about it. Take a moment to think about it. And then I'm going to ask you to share with me your solution. How would you think about how you would achieve something like this, something like a cert, but protection for that response, that IP address of mail.google.com. Okay, so take 30 seconds and think about it.